Thank you. Okay, so this is, well, let me thank the organizers for the opportunity of talking about actually two works made in collaboration with people from Torino. Oh, maybe this is Andrea, Michele, Elia, and Marco. Andrea and Elia are two PhDs. And it's actually two works, one about confining strings and one about the critical Casimir effect, and the one about the Casimir is ongoing, work in progress. Okay, both of these two works actually would be either very expensive to do, or actually probably just impossible to do with a standard Monte Carlo. Okay, so let's just revisit what a standard Monte Carlo, Markov chain Monte Carlo works. The idea is that we want to sample from a probability distribution P, and actually a very efficient way to do so usually is through a Markov chain. And when you do every time you do a Markov chain, you usually undergo a thermalization process. So you start from some random or some cold configuration phi, and then you just apply what we call the transition probability, which is defined according to some equilibrium distribution P, and under certain criteria of the Markov chain, antecedent conditions, you know that at some point the Markov chain will converge to the equilibrium distribution that you want. Okay. Now, the idea is that eventually you will compute your observables of interest on the equilibrium distributions, or the equilibrium, configurations. Now, there are several issues about Monte Carlo. During this workshop, we have seen a few, for example, sign products. In this case, these are not so bad, I would say, but still worth investigating. The first one is that actually all this is not very well suited to compute partition functions, even ratios of partition functions. What you actually do is that sometimes you, for example, the integral method, you compute the derivative of the partition function with respect to some parameter, and then you integrate back, but it's a bit cumbersome. I mean, it kind of works, but it's quite expensive. The other thing, which is probably even worse, is called critical slowing down. The idea is that when you compute a certain observable on your, say, thermalized configurations, the subsequent configurations actually are extremely correlated with each other. These are, well, usually the most famous one is topological charge in QCD or in LDS. And this happens when you move towards a critical point. For example, in lattice QCD, when you move towards the continuum limit, the topological charge exhibits this possibly exponentially increasing autocorrelations. So I think both of these issues can actually be tackled by relaxing one of the criteria about the equilibrium Monte Carlo, and the idea that we want to go out of equilibrium. So what I'm going to explain in the next 5 to 10 minutes is how to work out a framework to do an out of equilibrium Monte Carlo simulations. And the idea is that we are going to start from a prior distribution, I'm calling Q0 for now, and then ending up our target distribution, which I still calling P. And in order to do that, I'm interpolating between these two distributions with some intermediate, in this case Hamiltonians, which depend on some parameters, the parameter C of n, which I will call the protocol. Okay? So you have to imagine such an interpolation, such a sequence of distributions which interpolate between prior and target. Okay. This is a small cartoon, what I would like to do. I start from my prior distribution down here. This is at equilibrium. This has been either thermalized or a distribution like a random number, something that you have control of. And then you start, first of all, you change the protocol parameter. So you make this move. And then you start updating the system with the new protocol parameters. This makes the system automatically out of equilibrium because you thermalize the system with C of n minus 1 in this case, and then you're updating it using C of n. And C of n, I don't know, could be beta, could be some boundary conditions, whatever you can think of in your Hamiltonian or in your action, whatever parameter you can think of. And you repeat it n step times until you reach the target. So you go up here. All these red diamonds are out of equilibrium updates with an ever-changing Hamiltonian. And what you compute overall is a kind of a weighting factor, but a more generalized version if you want, which I call the work. And this thermodynamic term actually makes sense because it is literally the external work I'm doing on the system every time I change the parameter. This is computed over the same configuration, okay? This is a string configuration, for example, and this is while changing the some parameter in your Hamiltonian to the next step. Okay. These are actually what an out of equilibrium full simulation looks like. So we have some prior distribution at equilibrium, and every once in a while you pick one starting configuration, then you move out of equilibrium, you perform your evolution along this one, you compute the work several times for each of them, and then if you have some observable of interest that you want to compute at the target distribution over here, then you also compute it, of course. Okay, now what does it do? I mean, why do this? The point is that we can, if you use this framework, you can use a very powerful result from non-Euclidean statistical mechanics, a fluctuation theorem really, which is just density equality, which is also, well, 28 years old. The idea is that if you perform the average over all these different evolutions of the exponential minus the work, what you get automatically is the ratio of the two partition functions, where the z0 is the partition function of this distribution here, and z is the partition function of the target distribution up there. Okay, and this you get it directly. Okay, so this is the way to compute a ratio partition function or a difference in free energy through a Monte Carlo simulation. And I think this is also already quite interesting and amusing. This is you can think of this. Well, this is actually a very famous result. Is probably also true in real life. People have been using it in microscopic experiments for RNA, proteins, this kind of stuff. Also very much used in computational chemistry, and statistical mechanics, of course. And you can think of it as a generalization of the second law of thermodynamics, because just by applying the Jensen's inequality, you get the second law of thermodynamics for isothermal transformation, which is our case. Okay. Yeah.
Does the equality assume that you let it equilibrate at each step?
No. In principle, it always, there is the extreme version in which you go immediately to the target distribution, that literally what we call reweighting, statistical mechanics. The point is that you have limited statistics. So the point is having this average work on limited statistics, and this happens, the closer you are to the equilibrium, the better, but not necessarily. This is true in principle for any kind of evolution. Okay. Okay, so let me tackle the two problems and two issues I mentioned before. So partition functions, so we can definitely use this. And I will also show you how we can actually systematically improve this. And there has been quite a lot of work, especially from the group in Turin, about this. This is almost a decade old. This was essentially my PhD thesis. The equation of state for SU3 pure gauge in 4 dimensions, because of course from the free energy you can get the pressure. The running coupling from Schrödinger functional, entanglement entropy, this has been worked by Andrea and Marco lately, through the replica trick. And in this talk, we talk about the critical Casimir effect. If you actually look at the actual sampling, so the critical slowing down, you can see that there is a reweighting-like formula for any observable that you can think of, like, for example, a topological charge for something which is suffers from critical slowing down. And the idea, of course, is that here you have to choose something, a distribution which has a easy, like it's not, has good autocorrelations, let's say, and something which has very bad autocorrelations, badly behaving. And if you do that, you can actually rework this in a way, a different way of sampling the target distribution. Okay, and this is very close to the idea of the trivializing maps by Luschel, and also by the flow-based approaches, which has been quite popular in the lattice 50 community in the last 5 years. Same framework, really. And we already been using this with Claudio, which is in the audience, and also Davide, to attack topological freezing in CPN-1 models. The stochastic normalizing flows I will mention later. It's a generalization of all this business. And I will talk about this concerning the sampling of the Nambu-Goto string on the lattice in the second part of the talk. Okay, so Casimir effect. The idea is that we are going to look at vector models, so this is the Hamiltonian, and most importantly, we're looking at a film geometry. So we have a very large area and a thickness of the system which is smaller than the other 2 dimensions. Okay, typical of the Casimir effect. This is a definition of the Casimir force that we can give. It's essentially the derivative of a free energy. This is F here, it's a free energy density, actually the derivative of Lz times the free energy density. Well, you also have removed this F bulk, which is the bulk free energy density. We know from Fine-size scaling that this is the expected behavior of the Casimir force. And if you actually go to the critical point, is where we want to go, really, you can show that this is, well, you can find the rather famous universal amplitude. And our idea was using, I will show you how in a second, these auto-equilibrium simulations to compute this delta for increasing n. And 1, 2, 3, we go up to 6. And the idea is also to understand if we can match from results for large n. Okay, so this is what we want. Okay, so in particular, this derivative here. This is a derivative with respect to a dimension in our system, so it's a discrete value. And one way to write it down is to write the discrete derivative of this object here. And you can rewrite this as these ratios of partition functions. Okay, this is fine by itself. This was essentially done with the integral method that I mentioned before some years ago by the group of Vasiliev and Gambassi. And the idea here is that you start from a system which has these dimensions, Lx, Ly, and Lz, and you move to a system which has one slab less. So you're literally moving from your system, you're stripping away from your system a two-dimensional slab. And this is what we could do, but this requires, if you want the Casimir energy, we have to remove F bulk. It's another problem that you didn't want to tackle. So what we are going to do now is to take the derivative again of the Casimir energy. This is the expected scaling at the critical point. And this is literally the second derivative of a partition function. And now it gets a bit complicated, but also a bit more fun. I'm going to write this second derivative here of this free energy in this way. This is just a standard discrete derivative of a discrete second derivative. And this is the ratio of partition function that we're looking at. There are two lattices which have a size of the third direction, which is Lz minus 1. And then at the end, I've got one with Lz minus 2 and one with Lz. What does this mean? How can I actually compute this in a single Monte Carlo simulation? This is a bit interesting, and I've got a kind of an animation to do that. So this is our starting point. These are two lattices. They are both being simulated at the same time, but they are not coupled in any way with each other. Okay? And the red points are the protocol parameter that I was mentioning before. Okay? What I'm going to do in a simulation is I start from these at equilibrium, and then I start changing the couplings, and I start mixing them. So you could say that the red ones are getting weaker, and the blue ones that just appeared out of nowhere are getting stronger. And you keep going, you keep going until one slab is stripped away from one lattice and it goes to the other one. And this is the final stage, if you want. And this is exactly the partition function that we wanted. So these are the two partition functions that we wanted to compute the second derivative, and the one at the beginning is the one that we wanted at the denominator. And we did this. It actually works. It works remarkably well. It's not even that expensive. And this is the second derivative. So these are all points calculated from different Monte Carlo, out of equilibrium Monte Carlo simulations. This is for O1, and this is already the finite size effect. So essentially we have to fit the finite size effects. The idea is that our delta over here would be essentially the asymptotic behavior of this curve for a large Lz, and we did this for O1, O2, O3, O4, and O6. Okay, and we perform this finite size effect, and then we can look at the results plotted up against 1 over n. And okay, we comment a little bit. These are preliminary results. We're sorting out the details here. The orange points are our results. There are two determinations from Monte Carlo, which are the blue points. Now, you might be worried that there is something going on here. Actually, the difference here is actually just due to a different treatment of finite size effects. So this is actually beyond what I want to talk about. We actually performed the same finite size effect analysis they did, and we tried to do that, and the results agreed, but we believe our treatment is more conservative and more correct. And also you can look, of course, at the n to infinity limit, which was computed a few times, also quite recently by Lu and Wang, which is the dashed black line, and also the 1 over correction, which was also computed recently, and it is this line here. And you might say that we are kind of approaching the 1 over, well, the large n behavior. Okay. This essentially ends my first part. The second part, I wanted to talk a little bit about something a bit different, which is a bit still related to computing partition functions, but also related to, yeah.
I got confused by this plot. You said you're approaching the large n line, but it looks like you're going away from it, no?
Yeah, the arrows are a bit large, so I would say it's inconclusive. I would say the most conservative. But the point is that it's a bit weirder because the Ising point already lies on the large n. And then it goes up, then we try to understand, well, you will need O10. Okay. So yeah, second part, confining strings. So the idea was to essentially simulate the effective string theory. So what is effective string theory for the people who are not familiar with it? The idea is essentially the following. You start from, well, an effective string theory. In the simplest case, you get the Lambo-Goto theory, so the bosonic string theory of a relativistic string. And you essentially, the partition function of this action can be matched with essentially the expectation value of either Polyakov loop correlators or a Wilson loop in the gauge theory, in Yang-Mills. Okay? This has had an enormous success in the last 30 years, I would say, especially when computing Z, as you know analytically extremely well. But of course, there are also some other observables which are kind of phenomenologically interesting. For example, the width of the flux tube, which can also be in principle computed in effective string theory, but it's a bit more complicated to do analytically. And also you can think of, of course, more complicated actions, because we already know that Lambo-Goto action is not the correct one, and which also quite a bit more difficult to handle analytically. So we tried a kind of a complementary numerical approach. We probably will never substitute the analytical one, but will help us in understanding a few things, and to put this theory on the lattice. Okay, so not the Yang-Mills theory, which I'm not touching now, but the Lambo-Goto one. And you can write the action of the worksheet. The worksheet of the Lambo-Goto, this we know it very well in the physical gauge, and you can just exercise it on the lattice. Okay, and this is what comes up. So we are going to simulate this theory here. It's essentially a scalar field phi, which in the 3 dimension actually. So we just have one field, and we impose the initial boundary conditions in the space direction because we want 2 color sources with 2 quarks on the boundaries, and the periodic boundary conditions in the other direction. Okay. You could think, okay, you can try to do that, try to do the standard Monte Carlo. And what happens? It doesn't work. There is a very severe critical slowing down. It actually goes in 2 directions. When you essentially increase the size of the system, this is one way to take the continuum limit, essentially, the autocorrelations increase quite a bit. But if you go to values of the string tension, which is essentially the parameter in your action, which are relatively small, and well, actually we want to go here because essentially this is where Yang-Mills is, they also increase exponentially. So there is like a double critical slowing down, which is terrible, and you can never do an HNC over this and get something meaningful out of it. So we tried something a bit more complicated, well, not really super complicated, which is a generalization of what I explained to you before. Before I had just a non-equilibrium evolution, just Monte Carlo steps. What I'm doing right now, I'm not going too much into details right now, but I'm using a stochastic normalizing flow. This is, I would say, a bit of a generalization of what we are doing, because we are not just doing the non-equilibrium updates, but we're also doing some transformations, some deterministic transformations, which are parameterized by neural networks. So we're using a little bit of machine learning down here. And let me say that this is the only way to sample from this theory. Okay, just using Jasinski equality or this kind of stuff doesn't work by itself. Maybe it might work, but it requires a bit. One has to think about how I actually do it. Just using the neural networks doesn't work. You have to use both. Okay, so a combination of deterministic and stochastic approach. And the idea is that you are going to train all these layers, which are represented by these orange dots, by minimizing the work that I showed you before, which has to be generalized. This part here is the same one that I was telling you before, and plus there is the logarithm of the determinant of the Jacobian of each of these transformations, and by minimizing this object here, you can actually find the correct parameters for this transformation. And this is what we did. In this case, we are starting from the base distribution, pi distribution, which is a free boson, something that you know analytically, essentially. And you go to the target distribution, which is a Lambo-Goto with a given string tension. We chose to change 1 over sigma linearly across these transformations. Okay, the first thing that you want to do is whether we are doing something correctly or not. And the point is we can actually check it because we know very well the partition function. In particular, this goes with the this Wessel function. You can extract the energy levels from Nambu-Goto, and in the end, the larger R limit, you can find this behavior for the logarithm of the partition function. And you can check it out. We can compute the partition function using just equality. And essentially we found that you can clearly distinguish in both of these plots the behavior of the points are results of numerical results, and you can clearly distinguish the behavior of Nambu-Goto and one of the free boson, okay? Which is, for example, a good way to see the difference, the fact that you're not just sampling the free boson, and in particular, if you fit these curves here, you can look it up. It's essentially this term here, which multiplies sigma of r. This is essentially the one multiplying the RLO. And this A0 is literally pi over 3, which is essentially where the Lucier term comes from, which is comes from here. Okay, so this works. We are doing everything apparently correctly, and so we can look at something that you cannot compute analytically. For example, the string the width of the string, which is quite interesting because this has a nice counterpart also in Yang-Mills theories. You can also compute it, and has been done several times for gauge theories. And this is a snapshot of the worksheet that you're doing. The yellow points are the two color sources, the two quarks. And what we're going to do is to essentially measure the phi squared over the central points here. This is essentially the same thing that you would do on a gauge theory. Well, it's a corresponding one. So we do this. There is a perturbable calculation in 1 over sigma made by Nando-Gliozzi some time ago regarding this observable here, and Michele some time ago actually conjectured that you could resum the terms multiplying r in this way. So this is the same 1 over the same square root appears as it appeared in the partition function, and you can actually look it up now numerically and see if this square root actually appears. So we took the data, we fitted this data, and you can see that this F0 actually again agrees with pi over 3. And so we essentially are giving numerical confirmation of a conjecture, you might call it, concerning the behavior of the string width for Nambu-Goto. And okay, this is just an example. When you add also more terms to this is the case of extrinsic curvature to Nambu-Goto, and you can also play around with the more complicated theories. But I guess I can also jump to the conclusions. So this talk was the idea of this talk was to showcase what you can get by giving up the idea of doing all your Monte Carlo simulations at equilibrium. And at equilibrium, and then performing them out of equilibrium. And first of all, justice equality is the natural way to compute ratios of partition functions, and I think has several applications. And if you have more, we can discuss them. We'll be very curious. And in the case of the Casimir force, there was this complicated second derivative which depended on these strange ratios of partition functions, and this works spectacularly well. And something even possibly a bit more ambitious than mitigating its critical slowing down. So essentially, these non-equilibrium evolutions and also this generalization, this systematic improvement, which is a stochastic normalizing flow, is a very, very efficient tool. It requires a bit of training, but not that much. And most importantly, I didn't mention it, but it scales very well when you increase the volume size, or anyway, when you increase the degrees of freedom in your theory. And essentially next is tackling more seriously topological freezing in Yang-Mills. This is what we are set out to do this year. And we are thinking about larger scale implementation of all these in 4 dimensions. And the idea here is that on the base distribution, the one that behaves well for the critical slowing down, we have open boundary conditions that they correlate the topological charge. And then you move towards periodic boundary conditions where the topological charge has a possibly exponentially increasing integrated operation. And we can systematically improve this with the stochastic normalization. So I guess I'm done. Thank you.
Thank you for a very interesting talk. We have time for some questions. Okay, see one in the back.
So I have 2 questions. First is that how is your numerical result, this Monte Carlo, compared to the TBA methods for the excited state energy?
There is a recent determination for the, you mean for the Casimir energy, right? There is a recent determination coming from the thermal bootstrap, I'm aware. It's quite recent, I think.
I mean from this thermodynamic beta that's
concerning, I'm not aware of those results. I'm aware of more recent results coming from the thermal bootstrap from December, from the group in Hamburg, which we have been discussing with them because we are trying to understand how to make them, but I'm not aware of those results.
I mean flux tube thing, maybe not this plot. I mean the effective string, excited state energy of the effective string theory.
Sorry, I misunderstood. We haven't checked that, but I think it would be a bit complicated to do that.
Okay.
The excited state, I think we don't reach the precision yet that we can. Sorry, misunderstood.
Yeah. My second question is I'm just confused about the origin of the stochastic, because like effective string theory seems just perfectly unitary. Why there's a stochastic method for that?
Oh well, I mean it's when you look at it, this is an action, and you might say I can try and do a Monte Carlo out of it. And see what happens. The Monte Carlo is intrinsically stochastic. The idea of the Monte Carlo is that you're just generating configurations of the fluctuation of the string, if you want, and on the worksheet. And in principle, it should work. I think just using a normal Monte Carlo, I mean, maybe it's related to what you were thinking. It doesn't really work, maybe also because of that reason, because the excitations are a bit. But in principle, I don't know why you shouldn't be doing that.
Maybe Yuya was next, and then Victor.
So could you make a comment on comparison with, for example, parallel tempering methods?
Oh yeah, sure. So parallel tempering, I would say they're very, very similar. Parallel tempering is extremely efficient also in this case. They work quite similarly in the end. The point is that with the parallel tempering, you have like all these different replicas, all these lattices that you have to compute simulate at the same time, and the number of replicas has to increase a little bit, especially for like partition distributions which are a bit far away. And if you're doing like a large-scale simulations, this is a problem in memory essentially. It'll like compute a CPU memory, and so at some point this is like it could be in principle too large. But in the end, they are quite similar because in the parallel tempering, you have to look at the acceptance rate when you jump from one replica to the other. And this is not too dissimilar to what we are doing when essentially looking at the work in particular. They are related, not so easy to understand how, but they're related. Yeah.
So when you say you expect that putting number-God action on the lattice should work, like why the naive expectation that it shouldn't work, right? Because it's non-renormalizable theory, and that's why your naive Monte Carlo fails, right? So that's not surprising. So now you're using this stochastic thing is some regularization that seems relatively random.
Yeah, I think the point is that we kind of know how the partition function actually looks like in the continuum, so we can actually just look at the relevant terms in the partition function, and then.
I don't think you know. I mean, this is some calculation that is not clear how it's related to number-God action in 3 dimensions, right? Because to get this result, you use Polyakov action, but it's not very clear what the status is.
Okay, maybe we can discuss it. Maybe you can.
And I mean, it seems like if this works, why not put like Einstein-Hilbert action in 4 dimensions on the lattice and then simulate, right?
Yeah,
so
okay.
It's the same thing.
Yeah, sure. Maybe.
Okay, John. I have a question about the first part. So I guess it's related to Yuya's question. So you're coupling the 2 copies at intermediate steps, right? So like space is no longer a manifold, really. It's like not an approximation of a manifold.
Yeah, absolutely. Is there something at any point it is essentially physical?
It's sort of locally higher dimensional. Right?
Yeah.
So I guess there's no. I can't think of it as some like replicated path integral.
Could be. I usually have a hard time understanding what actually happens here, like on a more theoretical level. But if you have ideas, I would be happy to hear them, actually. The point is that everything that happens here, you don't really care as long as you can actually reweight on the target distribution at the end, which is the only one that has to be physical to some extent. What happens in between will actually be useful to actually model it.
And it doesn't matter like which parts of the thing you attach to each other?
Well, in this case, it has to be like this. But in principle, you can, I guess, yeah, there is a bit of freedom in how you actually choose the protocol. Yes. Yeah. I mean, like initial and final point has to be fixed. Whatever you do in between, it's a matter of efficiency.
So I also have a question.
Yeah.
So you've advertised this as a powerful way to solve critical slowing down problems, or? So I have two questions. So one, is it solving the critical slowing down problem, or is it mitigating it? Is it just changing the exponent? Is it mitigating it?
I would say, yeah, mitigating it, to bring it now to a practical application. In the end, anytime you go to the continuum, for example, you will have some sort of critical.
Good. I figured, I mean, mitigating is good enough if it works.
Sure, exactly.
My next question is, perhaps the most famous critical slowing down problem, at least that I heard about, is the one that occurs with like when you approach a critical point. So, for example, in QCD, light fermions are very expensive, very roughly, because of critical slowing down.
Absolutely.
Can you apply this?
In principle, yes. What you would do in that case would be to, well, set the fermion mass a bit larger, where you don't have that problem, and then go to the point, like the pointer, like maybe a physical point, for example, for like some lines of constant physics. That's what I would do, but maybe not the most efficient way. And then in that case, unless you, of course, are changing the gauge coupling and the Bayer quark masses at the same time, so you have more than one parameter, and you would do that. I think, yeah, whenever we go to QCD, that will be the way to do it.
I mean, before breaking out the heavy machinery and going to QCD, you could test it in lower dimensional models. I mean, and if it works, that would be very persuasive evidence.
I mean, in the end, I think it has to work, and then everyone has to see whether it's actually efficient.
That's what I said. That's what I mean by work. Yes. Is it actually a speed up? Yeah. More questions? I think people might be very hungry. So perhaps we should pause here, and you can ask Alessandro more questions during lunchtime. Thank you.